Welcome back. So we are still ahead of schedule, which is good. So I'm going to try and make sure we finish at least 3.2 and maybe start 3.3. Uh, just get the gist of it started. And then with any extra time, we might go ahead and take some time to do a little bit of review. So find the absolute extrema. Let's go back because I realize I know this every single semester that course that the semi. Let me guess. Are we kind of still feeling a little bit iffy on the semi-critical versus critical value situation? Does it still feel a little weird? It's okay if it does. It's definitely strange when you first encounter it. So especially I'm causing this confusion now so that we're not confused later, and we don't get. I'm trying to think of a good analogy. Like maybe it's with like this is a very bad analogy because I don't play basketball, but I'm pretty sure like if I remember correctly, when you're shooting a hoop, as they call it, right? You're supposed to use your legs a lot to do the shot, correct?
Yep.
So if you like when I learned it, I didn't get that proper form, and so I'm trying to shoot the ball with just my hands, and I'm screwing up. And I remember talking to a friend, and he's like, "No, you got to use your legs." And so it was harder for me to learn that because I was so used to doing it a certain way earlier on. And so, in the same vein of that situation, I want us to be cognizant. I want us to be aware of semi-critical values for when they become useful in unit 3.3. So, a semi-critical. Oh, go ahead, Luke.
Sorry. Use minus the ones that are wait. One of them it had to do with domain, right? Semi-critical includes ones outside of the domain.
Exactly right. So, as an example, maybe this will also help make it a little more clear. So, if I were to show you this graph, let's draw a curve like this. And then let's add a vertical asymptote right here. And go like that, and then go like this. Like that. Let's just say right now that's your curve. So this function has two critical values, or two semi-critical values, one critical value. The critical value is right here because that's a place where the derivative would be equal to 0 because you have a tangent line there. That's horizontal tangent line. And then the other one that's a semi-critical value, but not a critical value, is right here. I'm going to actually change it just a smidgen because it does play a role. So I'm going to go like this. So when we talk about 3.3, when we get there, we're going to be studying whether or not something changes when you're increasing or decreasing. And the critical value, the actual relative maximum right here, at this critical value, you see that it changes from increasing to decreasing. And then at the semi-critical value, a place where the function doesn't exist, it's got a vertical asymptote there, it changes again from decreasing to increasing. That means that a semi-critical value plays a role in determining where a function's increasing or decreasing. So even though it doesn't give us a relative extremum, even though it doesn't like give us anything at that value, it tells us about the graph on the left and the right-hand sides of it. So semi-critical values still play an important role in determining properties about a function. So that's why I want us to study them right now, even though they're not going to be useful when it comes to finding absolute extremum. Absolute extremum, you're only worried about critical values. But when it comes to increasing and decreasing and relative extrema, they do play a role. So that is why I want to talk about them before we get to that spot. But anyways, the main key difference is that at critical value, your function has to exist there. Whereas with a semi-critical value, your function doesn't have to, but it still plays a role. So when you're finding critical values, like finding semi-critical and critical values, it's the exact same process. Find the derivative, set it equal to 0, and find out where it doesn't exist. The only thing that you need to check at the end of the day is whether or not the function, the original function, exists there. This example was a prime example of critical values versus semi-critical. When we found that like the derivative was given to us, we set it equal to 0 or where it doesn't exist. It equals 0 where the numerator equals 0, which would be at -7/2 and at -1. And then at -2 and at 4, it does not exist. So those are all semi-critical values, because every critical value is a semi-critical. Every critical value is contained in the semi-critical values. But -2 and 4 make the original function undefined. So they play a role in terms of increasing, decreasing behavior, but in terms of whether or not a function has a relative extremum there or an absolute extremum there, they don't do anything for that. So anyways, the whole point of this section was to get to the extreme value theorem, the EVT, as we sometimes call it. I should probably write that just so that I don't have to write extreme value theorem every time. EVT. And so the way it works is the extreme value theorem says that your absolute extrema on an enclosed interval will either occur at an endpoint or at a critical value within your thing. It doesn't tell you which one it's going to be. It doesn't say where it is. It just says that it will be one of those values. It'll either be an endpoint or at a critical value within the interval. So that's what step 1 and step 2 are doing. They're trying to make you find the critical values in the interval. Step 3 is then saying, I don't know which one it's going to be, so I'm going to evaluate the function at all those spots to see which one gives me the largest value, which will be the absolute maximum, and which one gives me the smallest or the most negative value, which will be the absolute minimum. So on this problem right here, find the absolute extrema of this function, L of x is equal to 1/3 x cubed minus 2x squared plus 6x minus 6 ln of x plus 1 on the closed interval, bracket 1/2 to 3. So if we're going to find absolute extrema on a closed interval, we're using the extreme value theorem, which means we need to first find critical values. In this section, by the way, in unit 3, when it comes to the exams, it's always a good bet to take a derivative. You're at least guaranteed 1 or 2 partial credit points if you take a derivative. So just keep that in mind. But we got to find the critical values. So we'll find L prime of x. And so that would be x squared minus 4x plus 6 minus 6 over x plus 1. Technically, that's a chain rule, that last piece. Technically, it's a chain rule, right? Because you should have, you should be multiplying by 1, but that doesn't do anything. If it was, just as a reminder, if it was 6 ln of 2x plus 1, then the derivative of that would be 6 over 2x plus 1 times 2. Just so we're clear. It's just because the coefficient in front of the x was 1, it didn't do anything. But anyways.
And that's also, could you technically take 6 times 1 over x plus 1? Right?
Exactly right. So, yeah. So let me delete that. And so we're going to, if we're going to find critical values, we're going to set the derivative. So L prime equal to 0 / d and e. That's x squared. And I want you to leave a little bit of space, then write minus 4x, then leave a little bit of space, then write plus 6, and then leave a little bit of space, and then write minus 6x plus 1. We're setting that equal to 0 or where it doesn't exist, or d and e. You don't need to write the or d and e. You don't need to write the L prime equals 0 / d and e. It's just for our notes to say, like, this is what we're doing. So we need to solve that equation. And in its current format, there's no easy way to do it. But as soon as I see a fraction, what's the first thing that should pop into your mind? Say what? Common denominator, right? Good job. Round of applause for Diego. I got this at Chuck E. Cheese for 60 tickets, guys. That was a 60 ticket joke right there. So, boom. So worth it. Worth every cent. So I'm going to multiply this by x plus 1 over x plus 1, this by x plus 1 over x plus 1, and this by x plus 1 over x plus 1 to get the common denominator. Now, one student may ask, or you might be wondering, why didn't you just multiply by x plus 1 to both sides of the equation to get rid of that denominator?
Same thing.
Because it would give you the same solutions. However, you'd lose out on -1. So if I were to multiply both sides by x plus 1, then I just have just the numerators with no x plus 1. And that x plus 1 is going to play a role later on. So I'm not going to do it that way. I'm going to try and keep it all together so that I can utilize it. You'll see once we get to unit 3.3 why I'm going to do that. So I don't recommend solving it that way, which is frustrating because that's the way we've learned it. But as I said, that x plus 1 is going to play a role later on, so we're going to keep it around. So we get x cubed plus x squared minus 4x squared minus 4x plus 6x plus 6 minus 6, all divided by x plus 1 is equal to 0. Once again, the reason why I'm not multiplying both sides by x plus 1 is that multiplying by a variable does make you lose information. Yes.
What do you think about that? Because doing that might get us closer to the solution, but the solution's not actually the extrema.
So what it will do, it's so hard to describe without getting into the next section, without getting into 3.3. But I'll do a brief run through once we simplify this and factor it. So, so we do this, we get x cubed minus 3x squared plus 2x, all divided by x plus 1 equals 0. And that factors pretty nicely. You can factor out a common factor of x. And then that's x squared minus 3x plus 2, which factors to x minus 1 times x minus 2, all divided by x plus 1 equals 0. Any questions on that so far? On that algebra? So, to answer Louis' question about why we didn't, if we multiplied by x plus 1 throughout the entire thing, if we multiplied this part of the equation by x plus 1, all we would get is this, which would mean that all we get is this when we're solving it, which would make us lose out on the potential semi-critical, or it might be a critical value. It's neither in this case for weird reasons, but we lose out on that information. More specifically, when it comes into play in unit 3.3, what we're going to be doing is we're going to be solving a nonlinear inequality. If you guys remember those things, we had to solve things like x plus 5 times x minus 2 is greater than 0, right? And remember, you had to make that sign chart. And so if I don't have this, I'm missing out on whether or not that's positive or negative when I'm testing values. So there's a reason to keep it around. Anyways, so our semi-critical values are x equals 0, 1, 2, and -1. But the CVs, the critical values, are only places where the function exists. Does L of x exist at 0? Yeah. Natural log of 0 plus 1 is natural log of 1, and natural log of 1 exists. So 0 is good, 1's also good, 2 is also good because natural log of 2 and 3 are well defined, but natural log of 0 doesn't exist. So our x equals 0, 1, and 2, not -1, because L of -1 DNE. Any questions on that?
That's a question.
Mhm.
So on all of these that we get for extreme if we have a fraction, we should LCD.
Yeah, common denominator. Yeah. Absolutely. Few and far between, but yes. Yeah. So those are the critical values, but only one of those is in that, or two of those are in the interval. These are in bracket 1/2 to 3. So we don't need to worry about 0. If the interval was from 0 to 3, we test all 3 of them. But since it's from 1/2 to 3, we're only going to test those second 2. So we found the critical values. Now the extreme value theorem says that the absolute extrema are going to occur either at the endpoints, either at 1/2 or 3, or at the critical values within. So we need to test them in the function to find out which. So we're going to be testing it in the original function because that's the thing that we're trying to find absolute extrema for. So L of 1/2 is 1/3 times 1/2 cubed minus 2 times 1/2 squared plus 6 times 1/2 minus 6 ln of 1/2 plus 1, which is approximately, because I don't know what natural log of 3/2 is off the top of my head, so I'm going to bust this into my calculator. And in case you didn't know, so these calculators, you can always press up. After you've computed something, you can press up or back, and it'll go back to the same thing you entered, and then you can change the numbers. So I'm going to show you that on the, sadly, people watching the recording, you don't get to see this, but you can always ask me later on and I'll show you. So I'm going to switch it over real quick to the document camera. Let me zoom in. Zoom in, please. All right. You guys can all see that? So 1/3 times in parentheses 0.5 cubed. And then it's minus 2 times 0.5 squared plus 6 times 0.5 minus 6 times natural log of 0.5 plus 1. And so I'm going to enter that in. So I get that number. So let's just write out 4 decimal places, whatever you want to do, approximately 0.1089. Then I'm going to need to plug in the other endpoint, or I can, like, whichever one you do, like, you can do them in any order you want. I'm going to do the endpoints and then the critical values. So the other endpoint's 3. So what I can do now is I can just press back. And now I'm back in the equation, or I can press, and then I can just move in, delete this number, replace it with a 3. Instead of rewriting the whole thing, I can just start replacing it with the 3. It's not wrong to do it the other way. It's just, it's more tedious. I find this to be less tedious. So L of 3, I'm going to switch back to the, unless there's any questions on that. This is a little tidbit on how to use your calculator efficiently. So L of 3 is approximately 0.6822. And so those are the endpoints. And then we'll do L of 1, which is going to be approximately, if I plug that into my calculator, bear with me. If anybody beats me to it, though, let me know. L of 1 is roughly 0.1745. And L of 2 is approximately 0.0750, approximately. All right. So the absolute max then would be at the right endpoint, the 3. So ABS max at 3, 0.6822, and an absolute min at 0.0750. That's going to be the smallest value there. So L of 2. So 2, 0.0750 approximately. Those are our absolute extrema. You're going to start seeing it now, and the reason why I have had a hard time creating problems for this section. But just suffice it to say, in the previous section with unit 2, I can just make up a function whatever I want, right? And say find the derivative. It doesn't necessarily need to be factorable. But now in this section, I need it to not only to be nicely, like a nice derivative, and nice enough. I'm not going to try and make it obscenely obnoxious to get the answer, to get the derivative, but it also needs to factor somewhat nicely. And that becomes a very, very challenging task to figure out. That's why I haven't finished this section. Been trying to for ages. Yes, Luke.
Super annoying question, but wouldn't the adds not be necessary in this? Because it would either be the max of the decimal at 3, or no.
It's fine either way. Like, so technically, like I'm saying the max is at this coordinate point with a maximum value of 0.6822, and it occurs at x equals 3.
Okay.
But as long as you like, I'll probably put it on the exam as absolute max colon, and then leave a spot for you to put it on the put it there.
As an ordered pair.
Yeah, as an ordered pair. And I will always make sure to put it in kind of like in italics and bold, saying write your answer as a coordinate point or just the x values or whatever. So I got this section done. This section was good, but the other ones not so much. And the answers though, so if you want to check, if you want to do any of these problems, feel free to check the answer with me, or you can also check it with like Desmos. A lot of these things you can use Desmos to find out where the maximums and minimums will be. But anyways, 3.2, the mean value theorem. Now, much like the inverse function theorem, in real life, mean value theorem doesn't do anything for us. The only time you're going to get to see see it in action is if you meet me in the street. That's legitimately the only time it's going to happen. If you are over at a Chuck E. Cheese, I'll bust this question out at you, and if you get it right, then I'll give you some of my tickets so you can get that big prize. You know, those 6,000 point prizes. But otherwise, you're never going to need this. You're never going to need this. But what I do want to talk about is the fact that the mean value theorem is very, 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 very important in proving things. There's a section in real analysis, which is like the main course you take in your 4th year of undergrad, and then you take it a bunch in grad school, like all the different parts of it. And basically, there's a mean value theorem for everything. There's a mean value theorem for disks. There's a mean value theorem for spheres. There's a mean value theorem for complex analysis. There's so many different mean value theorems because they're very central. Every single question in the section that has the mean value theorem, it uses the mean value theorem in some way, shape, or form. Every proof requires the mean value theorem. It's so important. It's so central. But its applications in real life are limited. So we're not going to spend too much time on it. But it says, let f be a continuous function on a closed interval and differentiable on the same interval, but the open version. So it doesn't necessarily need to be differentiable at the endpoints. It just needs to be differential on the inside of it. Then there exists at least one. There could be multiple, but there exists at least one value c within the interval such that f of b minus f of a over b minus a is equal to f prime of c. Or more usefully in proving things, f of b minus f of a is equal to f prime of c times b minus a. So what it's trying to tell you is that the slope of the so there is a point, there is an x value in a comma b such that m tan is equal to m secant. The average rate of change and the tangent lines are the same. So the slope of this line here is equal to f of b minus f of a over b minus a. That is the quintessential calculus graph, that little squiggly line. And so this thing is definitely continuous. It's definitely differentiable because it's very well rounded. There's no corners, there's no cusps, there's no discontinuities. And so it fits everything within the conditions of the mean value theorem. And you can see that there are two c values. There are 2 points where if I draw a tangent line right there, you'll see that it has a parallel tangent line. Let me get this. Similarly, we have this C value right there, and we have another tangent line that has the exact same slope. So these have the same slope as this. One of the most useful points of it is that if there's a continuation of it called Rolle's theorem that allows you to find critical values, but that's neither here nor there. We'll get to that. So I wanted to talk about why the suppositions are so important. So the fact it needs to be continuous on the closed interval and differentiable on the open interval itself. Why we need continuity. If I have this function here, that's not continuous. It has a jump discontinuity in between A and B. And if you look at it, if I were to draw the secant line, the secant line is 0. The secant line has a slope of 0, but there's no value for which there's no value between A and B for which the tangent line will have a slope of 0. No place on the graph, no x value where tan line has a slope of 0. Then why? Oh, yes, go ahead.
I'm sorry, can you remind me, tan line, I remember, what it is. What is secant line again?
The secant line is the average rate of change. It's the taking the difference between the like where you start and where you finish and finding the slope of that line.
Okay, that's
So-
new to today, right? The graph of secant?
The secant line, it's a 126 topic. And we briefly mentioned it in unit 2.1, which was talking about how the secant line relates to the tangent line. And this is a new connection between the two.
Say it one more time. It's the rate of change between what? Between the different, what is it?
It's the rate of change between the start, like the f of like A comma f of A and B comma f of B.
Oh.
So it's right here. So this is equal to m subsecant. Or m sub AVG, however you want to write it. I usually write it as average rate of change because m subsecant sounds so weird. Like a secant line doesn't sound make sense too much to me, but either way. Why do we need differentiability? So with this one, if you were to draw the secant line connecting the two endpoints, there's no x value that has that tangent line slope. There's no point on the graph where you would have a tangent line that has that shallow of a slope. All the negative tangent lines are on the left half before the cusp, and none of them will look like that. So that's why you need continuity and differentiability. But either way, verify that the conditions of the mean value theorem are satisfied for the function f of x is equal to x cubed minus 2x plus 1 on the interval 1 to 3, and then find all the c values that satisfy that conclusion. So f is a polynomial. Continuous and differentiable everywhere. Right? Polynomials are the nicest functions that we know of. They have derivatives. They have infinitely many derivatives. They're differentiable everywhere, and they are continuous everywhere. So it satisfies. So of course it's continuous on the closed interval 1 to 3 and differentiable on the open interval 1 to 3. So f prime of x is 3x squared minus 2x, or minus 2, excuse me. And then f of 3 is equal to 3 cubed minus 2 times 3 plus 1, which is 22, right? Because 9, 27 minus 6, that's 21 plus 1, 22. And f of 1 is equal to 0. So f of 3 minus f of 1 over 3 minus 1 is equal to 22 over 2, which is 11. All right, so it looks like I'm doing some random stuff. I know that. And I'm going to talk about what I'm doing in just a moment once you finish writing that down. The mean value theorem says that there is a point C such that f prime of C is equal to f of b minus f of a over b minus a. So in this case, I found the derivative because I'm going to need that. And then I found the f of b minus f of a over b minus a in that second portion. So by the MVT, f prime of c is equal to f of 3 minus f of 1 over 3 minus 1 for some c value. That is to say, 3c squared minus 2, that's the derivative evaluated at c, is going to equal 11. And so we can solve for c. That's a polynomial equation. We can either use the square root property, or you can factor it if you really want to. But I'm going to do the square root property. This tells me that 3c squared is equal to 13. It gets me c squared is equal to 13 thirds, which gives me that c is equal to plus or minus the square root of 13 thirds. Leave a little bit of space between your plus and your minus. Plus or minus, because only one of those it's a c value between a and b. There's only one of those numbers that's between 1 and 3. So we're going to cancel out the negative 1 because negative square root 13 thirds is not in 1 to 3. So the only c value, c equals square root 13 thirds, square root of 13 thirds. Any questions on that? I think I can definitively say you're probably not going to have any mean value theorem questions on your quizzes or exams. So I wouldn't worry too much about it, because once again, the only time this is going to happen in your real life is if you meet me at Chuck E. Cheese. So as long as you stay away from Chuck E. Cheese, you'll be safe. Which, I mean, their pizza's pretty dope. It's pretty lit AF, as the kids say, right? Lit. It's like surprisingly good, actually. Like I'm not even joking. I'm not trying to like be selling. They don't pay me for this situation, but like I was actually quite pleasantly surprised at how well their pizza, how good their pizza is. So unless you want to get some nice stuffed crust at Chuck E. Cheese at one point, you're probably never gonna have to see the mean value theorem again. Yes.
For like a couple weeks ago, I was supposed to see the transport debate. One of like the ads was like for Chuck E. Cheese, and I just felt so old because I'm just like I remember like going there when I was like 10.
Yeah, they're trying to do a rebranding, by the way. They're trying to do a rebranding. They're getting rid of the animatronics, trying to move away from the Five Nights at Freddy's situation. Which I kind of get.
Like I'm seeing the thing, I'm like, who's this guy, bro? Like,
Yeah. And they play a lot of songs in there that go on repeat. So I've got them quite memorized at this point. So it's playing over and over in my head. Anyways, let's go ahead. We're just gonna skip the applications. I don't even want to do them. Omit.
Let's just do this last problem and then we'll take a break and then we'll spend. What's 3 point? How does 3.3 start? Yeah. We'll spend the rest of the time doing review. So like, let's do this last problem from this just to show you how it works. So does the mean value theorem apply to f of x equals natural log of x on the following intervals? If not, explain why. So it does not apply for the first situation. No, because yep, f of x is not continuous at x equals 0 because f of 0 does not exist. So it won't fit into the mold. It doesn't, you need to be continuous on the closed interval, but f of 0 doesn't exist. So it's not continuous on that interval. In fact, it's also not differentiable because the derivative of that is 1 over x and 1 over 0 doesn't exist either. So it's not, oh, well, I mean, you don't need to be differentiable on, you don't need to be differential at the endpoint. So it's just not continuous there. However, on this next one, yes, it is. Because the function is continuous on its domain, and that's within its domain. And then the derivative, 1 over x, is defined for all those values. So yes for the second one. F prime of x is 1 over x. F of 7 is natural log of 7. F of 1 is natural log of 0, which is just, or sorry, natural log of 1, which is 0. So by the MVT, f prime of c is equal to f of 7 minus f of 1 over 7 minus 1. That's 1 over c is equal to natural log of 7 over 6. So that tells me that c is equal to 6 over natural log of 7. But let's go ahead and take a break. We'll come back at 12:10. And I'm looking at unit 3.3, and I don't want us to go over, we're gonna have to re-go over unit 3.3 stuff, even if like the beginning of it, even if we started off. So I'm just gonna leave that for Monday or Wednesday of next week.
Our exam's Monday, right?
Yes, your exam is Monday. So we're gonna come back at 2:10, and then any rest of the time we can do is for review for you guys. So we got a lucky situation, we got a lucky break, we got some time. So come back at 2:10 or 12:10, not 2:10. So I just wanted to spend the rest of the time going over review for the exam. So the exam covers, and I wanted to mention this right now. I think I mentioned it on the homepage, and I hope everyone saw my emails giving you guys the exam review along with its solution guide. So what I said during there is that unit 2.1, we technically covered the first part of that on exam 1. So there will be no definition of the derivative problems. However, there was a lot of material in 2.1. There was talking about tangent lines, and rates of change and things like that. So don't just assume that 2.1 you can skip. There is material in 2.1 that is important. Finding tangent lines, finding when tangent lines are certain, like whether when they're horizontal or when they have a slope of 5 or when they're parallel to something. So all that stuff is still important. It's just there will be no questions on the definition of the derivative. Is that clear? So otherwise, it's all fair game besides that. So 2.1, 2.2, 2.6, the only thing to worry about is the derivatives of the inverse trig, of which you only need to know sine, cosine, tangent, and cotangent. But if you know sine inverse and and tangent inverse, you automatically know cosine inverse and cotangent inverse. So basically, it all chops down to 2.4 and 2.5 and 2.7, because you can't do 2.4 unless you know 2.2 and 2.3, right? You can't do chain rules unless you know the product rule and the quotient rule and all the basic rules. Yes.
Can I ask you to do a second derivative? I just kept not like keeping when you do the first chain rule, it looked like from the answer key, I had to keep the first constant out front and then distribute it at the very end, but if you don't mind, I can give you a problem.
Sure. Is it from the notes or from the review?
It's from one of it's not from the review itself, no. It's
Okay.
from one of the exercises.
Sure, sure. From 2.4 or 2.3?
But I do have the problem here, though.
Okay.
It's second derivative of tangent squared of 3u.
Well, it's got to be 3.4 then. Jeez.
I'm sorry, and then not derivative, no, oh yeah.
It's right here. So derivative of tangent squared of 3u. Okay, that one. You have u is equal to tangent squared. So I'm just going to write tangent of 3u quantity squared. All right, I'm going to take that with me. Cut. No, I did not want to do that. And I wanted to do this one. Paste. All right, tangent of 3u, we're going to find the second derivative. So, first derivative, going to require a chain rule. T prime be 2 tangent of 3u times the derivative, d du of tangent of 3u, which I'm doing it in slow steps, but if you feel comfortable skipping that that step, please be my guest. So that's going to be tangent. So that's going to be 2 tangent of 3u times the derivative of tangent u would be secant squared of 3u times the derivative of 3u, so times 3. So there's a couple ways we could go about this. The secant is 1/cosine. So we could do it by combining the tangent and the secant and writing them as sines and cosines. That might be easier, but I don't know. I'm just going to simplify a little bit. I'm going to write this as 6 tangent of 3u times secant squared of 3u. And there's a lot of different ways we could go about this. We could either... So we can rewrite this as tangent of 6 tangent 3u times secant of 3u times secant of 3u. We could do that, and then we could do a product rule with a product rule inside it. That would be one option. But I'm going to go straight to chain rules. So what I'm going to do is I'm going to treat this as my f, and this is my g. Because remember, I'm trying to find the second derivative. I'm trying to find d squared t over du squared. So.
Because we already have the first derivative at that point.
We already have the first derivative. So f prime is going to be 6 secant squared of 3u times 3, which is 18 secant squared of 3u. And since g is equal to secant of 3u squared, g prime would require a chain rule with a chain rule inside it. So remember, whenever you've got the trig function with a number in between the trig function and the inside of the trig, it's like secant squared of 3u. Remember, that's really saying secant of 3u to the quantity square, secant 3u quantity squared. So it's going to require a chain rule. That's going to be 2 secant of 3u to the first power times the derivative of secant 3u. The derivative of secant of 3u would be, so the derivative of secant is secant of x tangent of x, but this is secant of 3u. So it's going to be secant of 3u times tangent of 3u times 3. That's going to be 6 secant squared of 3u tangent of 3u. Any questions so far? Then it is just a matter of doing the product rule. F prime g plus g prime f. So T double prime of u is equal to f prime g. So 18 secant squared of 3u times g, which is secant squared of 3u, plus g prime, which is 6 secant squared of 3u tangent of 3u, times f, which is 6 tangent of 3u. And so that's going to be, at the end of the day, that's 18 secant to the 4th of 3u plus 36 secant squared 3u tangent squared 3u. And that's T double prime. Is that what the answer is? Yay. I can do math. Always good to know that you can do math.
Yeah, I don't know what I was doing. I think I kept multiplying the 18 by the other sixes. But maybe I ended up doing it in my notes correctly, but why don't you, well, I guess because they're being added, the 18 to the 6 of them.
Yeah, because they're being added. They're separate terms.
And we can't combine them because that 6 secant squared 3u tangent 3u, that's like one term there, so you can't combine it with the, oh wait. You know what I mean? Like this,
Yeah.
I almost thought the secant squared with the 6 could be combined with the 18 secant squared, but you can't.
No, because they're separate terms. I mean, you can factor things out, and you can use trig formulas, by the way. You can use trig identities if you really want to bust out the, what is it? Secant squared is, oh, I forget this one. I can derive it. Sine squared plus cosine squared is equal to 1. So divide by cosine squared. So you get that tangent squared plus 1 is equal to secant squared. So you can definitely use your trig identities if you really want to, but that would be unnecessary. We don't need to do anything with this derivative, so we're all done. But that's a good practice problem for doing a second derivative.
This problem like 40 times. I can't remember it wrong, but I finally got it. But
Perseverance. It's good.
what about trying to figure out where the step would be, but multiplying to avoid having to do another product rule? Maybe I'll organize that better before I ask it. There was somewhere where they were like, well, I would multiply it to avoid another chain rule or something. But I'll try to figure out.
Yeah. There's the golden rule for this class, once again, for simplification, is only simplify when you need to use it for something. So if you need it, since we're needing to use it, I would simplify it as much as possible, but there's not really too much to simplify here. You could probably write it as sines and cosines, but I don't think that'll change much. I think that'll actually make it more difficult in the long run. Any other questions? Yes, right. 2.5. Sure, I can. 2.5, you said? 1i. Okay. I'm going to rewrite that. So x squared minus y squared. As soon as I saw that had a radical, I'm going to rewrite it in exponential form. So that's going to be 3x minus 2y to the 1/4. I started recording, correct? Yes, I did. Okay. No, not duplicate. Cut. I'm going to paste that on this document. Paste. So we want to find the derivative of this. We want to find dy dx. So first things first, we got to differentiate with respect to x. We got to do d dx. Remember, it's d dx, not dy dx. Dy dx is a derivative. D dx is the process of taking a derivative. So I'll put that d dx here, and the d dx has to go in front, like that. So the derivative of x squared would be 2x. The derivative of y squared would be 2y dy dx. So minus 2y dy dx equals the derivative of that. That is a chain rule. The outer function being the 1/4 power. So that's going to be 1/4 times 3x minus 2y to the negative 3/4 times 3 minus 2 dy dx. 3 minus 2 dy dx is the derivative of the inside of that thing. Now, there are many ways, once again, that we can solve this. We can solve for dy dx. We could, so as a note, you could rewrite this as 1 over the 4th root of 3x minus 2y to the 3rd power, which is probably what I'm going to do. But you could probably leave it as is as well. There's nothing wrong with that. So one option would be to multiply both sides by that, by the 4th root of 3x minus 2y to the 3rd power to cancel it out on the right-hand side. That would work, but there are so many different options. The brute force approach would be to distribute it in, which is probably what I'm going to do. Just do it by brute force instead of being clever. Because when it's come to exam time, I don't think we're trying to spend time being clever. We're trying to solve it as quick as possible. So that would mean that it'd be 2x minus 2y dy dx is equal to 3/4 times 3x minus 2y to the negative 3/4 minus 1/2 times 3x minus 2y to the negative 3/4 dy dx. I just distributed that 1/4 3x minus 2y to the negative 3/4 into the binomial term. No, it's not a binomial. It's the two-term thingy. It's not a polynomial. And then I've got to isolate those. So I could either bring all the dy dx terms to the right or to the left. It doesn't matter which way you guys want me to bring the dy dx, to the right or to the left. To the right. All righty then. So this will be 2x minus 3/4 times 3x minus 2y to the negative 3/4 is equal to 2y minus 1/2 times 3x minus 2y to the negative 3/4 in brackets dy dx. Like that. Finally, to solve for dy dx, I divide both sides to get the dy dx by itself. And get that dy dx is equal to 2x minus 3/4 times 3x minus 2y to the negative 3/4, all divided by 2y minus 1/2 times 3x minus 2y to the negative 3/4. And that is where we will leave it. There's nothing that can really cancel because there's no factors. You can only cancel factors, you can't cancel terms. So we can't just magically cancel that 3x minus 2y. That doesn't work.
And you can't get the whole thing in the. I know.
And this is fine. And believe me, if there is a problem on implicit differentiation, it probably will be, right? One of the sections, there's got to be at least one. And that's not me telling you as your teacher. That's me telling you as a former student. It's just logic dictates there's gonna be an implicit differentiation problem. It's 1/7 of the material. So yeah. And I will, so if there is one, I will be looking out for different ways to solve it. If you do different algebra, I will be looking at it and making sure that it's correct. And I will give you full credit regardless of how you come to the answer. As long as it's mathematically valid, I could not care less. Okay.
Couple questions.
Yes.
So right at the beginning, but I think you called it freshman's dream, right? But right at the beginning, I think I might have been inclined to put the 3x to the fourth power minus 2i to the fourth, but you can't because the whole
Yes.
thing is under the
Yes.
radical.
So that's just this is a very, very good thing to remind us. So don't write this down, but just as a reminder, a to the b times a to this wait. A times b raised to the n, that is a to the n, b to the n, versus a plus b to the n, that's going to be that binomial coefficient, a to the n, b to the n minus k, where k goes from 1 to n. So that's you cannot distribute the n into a sum or a difference of things. It only goes into the it's only when you're multiplying two things raised to a power. So
And the box answer right there, there's nothing you would want to do with rewriting it as the fourth root.
no, there's no need to.
Okay.
No
But
need
it's
to.
possible, but you shouldn't, because we're not using it.
Yeah, we're not using it, so there's no need to simplify it or write it any different. This is just as pretty as it's just maybe slightly same. It's trying to make a joke, but I couldn't think of it. Okay, any other ones? Related rates problem. Let's go over them once again. Things 2.2 is derivatives of basic derivative rules. 2.3 was the product and the quotient rules and higher order derivatives, so telling us that we can keep taking derivatives. 2.4 was the chain rule. 2.5 was implicit differentiation and therefore logarithmic differentiation. 2.6 was just the derivatives of the inverse trig functions. And then 2.7 was related rates. So that's kind of an overview of what's to come on the exam. Yes.
I had a question, I don't know if I'll say it effectively, but with the chain rule, I don't have a specific problem, but with the chain rule, let's say it's like there's three, like there's like a outside, inside, outside, inside, outside, inside. There's like three different functions in there.
Okay.
Doing the first derivative of a chain rule, even if it's like three inner outer functions, you exhaust the whole thing, right? So you don't do, for example, just the outer inner times the inner and stop with there being leftover functions. You have to do the
The whole thing. Yes.
and that's just the first derivative.
Yes.
Okay.
So let's do it. Let's do a good example of chain rule. Let's go a little, as the kids say, ham, right? We'll go ham. Right. So f of x, let's do sine of cosine of secant of the square root of x squared plus 1. So don't be scared. It will just be a little bit chaotic. And this is one of those ones where I might take it in steps, or you can just like stop, take a bite out of a granola bar after each outer derivative, whatever you want to do. So the outermost function is sine. So f prime of x, I don't even know why I labeled this question 1. Let's erase that. F prime of x, outer function sine. The derivative of sine is cosine. So this is cosine of secant of x squared plus 1 to the 1/2 times the derivative, ddx, of cosine of secant of x squared plus 1 to the 1/2. So I'm just taking care of it in steps. Next, we got to take the derivative of that thing. So we've got to do the outside function, the outer function's derivative. The derivative of cosine is negative sine. So rewrite the whole thing. So cosine of secant of x squared plus 1 to the 1/2 times parentheses, and I'm gonna be a stickler about this. Don't write this, because that looks like you're subtracting sign, especially if it gets too close together. So make sure there's a parenthesis. Sine of secant of x squared plus 1 to the 1/2 times the derivative of secant of x squared plus 1 to the 1/2. Whew. Okay, we're almost there. We're almost there. Because there's just two last chain rules. All right. So then it would be, so I'm going to start over here. So cosine of secant of x squared plus 1 to the 1/2. I'm going to put that negative sign right out front, actually, so I don't have to deal with that, times sine of secant of x squared plus 1 to the 1/2 times derivative of secant is secant tangent, not necessarily, like, technically it's secant of x tangent of x, so it should be secant of x squared plus 1 to the 1/2 times tangent of x squared plus 1 to the 1/2 times the derivative of x squared plus 1 to the 1/2, which would be 1/2 times x squared plus 1 to the negative 1/2 times 2x. And I would leave it like that because we don't need to use it for anything. But that is the answer. Chain rule within a chain rule within a chain rule within a chain rule.
That's just the first derivative.
That's just the first derivative. Lord help us if we're asked to find the second derivative. If I did that, that would be the whole exam. Just find that derivative, find the second derivative of that function. Whew. Could you imagine? That would be awful. That'd be fun though.
I don't know why at first I just kept thinking just do the first outer, first thing, and the times and then you're done.
Nope. Got to do it the whole time.
And then I just ask for reassurance, the bringing the negative out to the front from the negative sign.
Mhm.
Why does that not change all the signs? Is that because if you actually simplified it, it would, but at this point, it's just like -1 times everything as it is?
So yeah, it's just -1 times everything, and these are all being multiplied together. So by commutativity of multiplication, you can just jumble it, or well, more specifically by commutativity and associativity of multiplication, which in case, just so a reminder of what those mean. Commutativity means that you can multiply things in backwards or forwards. 2 times 3 is the same thing as 3 times 2. And then associativity means that you can multiply them however you want. As long as they're all multiplied together, you can multiply them however you want. So I just decided to move the -1 out front. But it's not required to do so. You could leave it in the inside. Just make sure you got the parentheses. Okay.
If there was another extra floating around, which there's not, but we would multiply them.
Mhm.
Okay.
And so, yes, technically the 1/2 and the 2 will cancel out. So if you want to, you can do that, but it's not required because we're not using this for anything. We're good right here.
If we did that, there'd just be a single X.
Yeah, there'd just be a single X. But that's good. So if you understand that problem, you got the chain rule on lockdown. You got the chain rule on lockdown. That's a lot of them. That's basically the question that was asked. Can you imagine trying to enter that into my lab? One mistake, one tiny mistake, all wrong. All that work just to get it wrong because you made an error. Oh man, I had to do that so often when I was a TA. I had to do that problem way too many times. So,
I've got one more if no one else has something, but I can.
so like, I'm happy to do it, but I like don't want to monopolize the time. Do you have one, Brian?
Question 3.
2.7 question 3. Get a 2. 2.7 question 3. Oh, this one. Forgotten about this one. So you have a ladder of unknown length L leaning up against a wall. You are pulling it away from the wall so that that one of the landers dragging along the ground at a rate of 0.4 meters per second. At the moment, You know what? I'm just gonna copy this. I think it'll let me do this. I love technology. Okay. You have a ladder of unknown length L leaning up against a wall, and you're pulling it away from the wall so that one end of the ladder is dragging along the ground at a rate of 0.4 meters per second. At the moment when the end of the ladder is 9 meters away from the wall, the other end of the ladder is moving down at a rate of 0.3 meters per second. Find the length L of the ladder. We'll need to find something before finding L. Okay, so let's go ahead and draw a picture because that'll help us figure things out. Here's our building. Here's our ladder. Pretty sweet ladder, if I do say so myself. Make the sounds as necessary. And so it's being pulled away, which means that this is going down. And this is an unknown length L. This is an unknown distance X, and this is an unknown distance Y. So what do we know? What do we want? So we know dx/dt is going to be 0.4 meters per second. We know dy/dt is negative 0.3 meters per second when the ladder is 9 feet away. Okay. So what we want is we want L. Okay. I'm gonna by the way, I haven't done this problem in a very, very long time, so we're gonna fumble around a little bit. We'll see what happens. I'm gonna try and use the Pythagorean theorem. That would be my first guess. So we know that x squared plus y squared is equal to L squared. And then, okay, we'll differentiate and see what happens. We get 2x times dx dt plus 2y dy dt equals 2L times dl dt, right? However, and you might be thinking to yourself, well, okay, the problem is here, so I know x, so, I should have written what we want. We want L, but we need to know a few things first. If I knew what y was when x is equal to 9, then I'd be able to find L, right? If I because I can this triangle will always happen regardless of what x and y are. They will always be solving the Pythagorean theorem. So if I knew, since I know x is going to be 9, if I know what y is, I'll be able to solve for L. But the problem is with this equation, I know x, I know dx dt, I know dy dt, but I don't know y, L, or dl dt. But I actually do know dl dt. What's dl dt? It's a fixed value. We don't know what L is, but the ladder isn't magically changing in size. So it's 0. dl dt is equal to 0 because the ladder is a fixed length. And that's the good news. That gets rid of L and dl dt. That means that there's only one variable left. There's y. And if I know y, then I can find L. So 2 times 9 times dx dt 0.4 is plus 2y times negative 0.3 is equal to 0. And so that's going to get me, so 2 times 9 times 0.4, 7.2. So 0.2 3 times 2 is negative 0.6. So negative 0.6y is equal to 7.2, negative 7.2, which gives me that y is equal to 1. And that will allow me to utilize, so now I know what y is. So x equals 9, y equals 1. With this together, I got 9 squared plus 1 squared is equal to L, which gives me that, or sorry, L squared. That gives me that L squared is equal to 81 plus 1 to 82. So L is equal to the square root of 82, which is approximately 9.05, near 9.06 meters. Is that the right answer? No?
It's nice and
12? It is 12. It is 12. I don't know what. Oh, I did answer. I had 7.2 was the answer of the previous thing. And then 0.6 was it. So I pressed answer divided by 0.6, but that would be 0.6 divided by 0.6, so 12. Thank you for catching that. So 12 squared. So not 182, but 81 plus 144 is 225. Oh, it's a Pythagorean triple. That's nice. L is equal to 15 then. Is that the right answer? Yes, I know how to do math. Yay. Cool problem though, right? Just it's a cheap shot. It's a cheap shot to tell you that like there's a hidden rate that you already know, the LDT. This would not be an exam problem. That's a very, very challenging one. Unless I made the exam only 4 questions, in which case then we'd have a long time to think about it before writing an answer. All right. Any other questions on this one? Main thing, they all get solved the same way, right? You always have to find an equation, differentiate it, and then plug things in. It's always the same. Just a matter of like, sometimes you need to go back to the drawing board. On these types of problems, if I were to give you my recommendation as a student, I would say with word problems such as this, put a dash next to it, come back to it. Let it like read the problem heavily, like take your time to read it, but don't start it unless you absolutely know where to go. Because you'd be surprised at how well your mind works in the back of your head. Like just put it in that slow cooker and let that just let that chuck roast slowly break apart so you can finally shred it. Or chicken, whatever meat choice you want. Just let that slow cook in the background. Okay. Louis, you had one question.
Not even a problem. Regarding the inverse trig functions,
Mhm.
do we seem to know those because you're gonna put those like in derivative problems or something?
Potentially.
What that?
I can neither confirm nor deny the existence of one on the exam, but it couldn't hurt to know them. Or you can just pray that it doesn't show up. And here's a big note about that. I mentioned it before, but once again, if you don't know the derivative of something, just write like derivative of this. Like say, like I don't know it, but this is what it's going to be. Like if this was the question on the exam, like y equals sine inverse of x squared plus 2 divided by x cubed plus 5. If you couldn't remember the derivative of sine inverse, what I would write on my exam is I'd write y prime is equal to deriv of sine inverse times 2x times x cubed plus 5 minus 3 times x squared, 3x squared sine inverse of x squared plus 2 divided by x cubed plus 5 squared. And then Sawi. But like you can do that and then you will get basically all credit. If you leave it blank, I can't give you anything. But if you show that you know, hey, I know how to do the quotient rule. I know how to do derivatives of basic functions. I know how to do the chain rule. I just don't remember the derivative of sine inverse. That, if that's a 10-point problem, that's an 8 out of 10 in my opinion. So, yes.
Like differentiations only with the variable and the exponent, and what was the other one?
The other one would be something that's obscenely obnoxious to take the derivative of. So like if your function was 2x plus 5 to the 13th power times e to the x plus 9 to the 7th divided by x to the 5th times natural log of x plus 7 times sine of 3x. Trying to do this by hand would be a tedious mess, because it would require a quotient rule with a product rule in the numerator and two product rules in the denominator, all with chain rules and just awfulness. But if you use logarithm differentiation, it'll break it up into nice, neat pieces. It's not wrong to do it that way, but it's just easier to do with log.
You need more than two rules in these models.
Yeah, anything more than about 2 or 3 different types of rules in a derivative problem, I'd use logarithm differentiation. Diego.
Points that you don't write solid.
Yes, no. All right, guys. If you have any questions, feel free to attend my office hours tomorrow or email me. I'm happy to answer any of the questions on the exam review or anything in general. Feel free to utilize those to aid your study. Remember that an exam review is not the only thing you should be doing. You should also be studying the exercises, going over your notes, and all that stuff. I'll be posting the quiz solutions very soon. If you have any questions, email me and attend those things. Otherwise, have a great day, great weekend, and I'll see you guys on Monday for the exam.